Hi, my name is Matt. We started a company 3 years ago, Magnitude Innovations, that helps people on doing complex applications, qualification, and troubleshooting in the AM space. We specifically work in the laser powder bed fusion on the metal side. So we have a team of 5 people. We specialize in a number of different areas. So one is material science, which is extremely important in this industry. The second one is aerospace, tooling, as well as the energy sector. And our approach is what we call agnostic, in the sense that we don't try to commit to working on any specific technology. We try to deliver the full solution to the customer that we work with. And we have a number of partners in our network that help us on certain applications where we don't really need to have the expertise in-house full-time. So our 2 product categories are focused on technical consulting and product development. On the technical consulting side, we help customers on the implementation of the technology, on the industrialization of the technology, and on any R&D topics that customers may have. On the product development, we actually deliver solutions so that if a customer has something that they want to develop and specialize in, so for example, hydraulic manifolds, we'll actually use our process knowledge in order to teach them about the entire value cycle so that they can, get the first project that they're going to be working on and have it be successful, rather than realize that they're missing something internally. The other thing that we do is develop software packages for our customers and new alloys. So one of the things that I really wanted to convey in this presentation is the idea that doing things right is just as valuable as not screwing up. And a lot of that comes down to the preparation that we do up front with the customer. So I'm going to go over some of these areas that we focus on, because when you just try and you fail, that's fine. Or if you try and succeed, that's great. But a lot of times there are things that we're not factoring in, and we make a huge investment into the technology or into the application or into the project that we're working on. And then we realize that actually we have to take a huge step back in order to make it successful. So the first thing I wanted to go over is the difference between parameter and material development. Now, on the parameter development side, we ask some very simple questions, which is, what is the root cause of the challenge that we're trying to solve? What is the balance between the parameter development set and, for example, heat treatment? Because sometimes we do parameter development and then we realize, actually, it's really a heat treatment issue and we didn't have to change any parameters. And the ultimate question in all that is, do we really need to do parameter development? Many times it's actually no. On the material development side, we have all of those things, but also we ask ourselves the fundamental question, is this actually feasible in AM? And are the material targets achievable? Because of course you can use parameters to improve material properties or make them more homogeneous, but sometimes it's just impossible with the technology. So of course, every process has its own advantages and disadvantages. On the laser powder bed fusion side, it's a rapid cooling process, and so things where rapid cooling is detrimental to what you're doing, it's maybe not the best solution. So on the parameter development side, we make a couple assumptions, which is that we have a fixed powder in terms of the chemistry, the particle size distribution, the morphology. We have fixed machine settings, which is typically the values that the machine manufacturer sets up, and we obviously don't mess around with, for example, the laser type. But there's also some things that we can optimize and tweak within those confines in order to actually get better material properties, or at least make sure that the material development work is successful. But in terms of parameter development, we leave all that constant. And to some extent, we also leave the layer thickness constant, because just as a general thing, when you increase the layer thickness, your parameter windows actually narrow. And so if you're building something in a 30 micron process and then you go to a 90 micron process, well, you're going to have a lot harder of a time finding the parameter window that will actually be good for your application and actually across all the other applications that you'll develop. On the material development side, we need to fulfill aerospace requirements, and that's our first and foremost requirement, right? So first and foremost focus. So that means qualification, characterization of the material across the powder bed, in the Z direction, across multiple machines, across powder batches, and that takes priority. It's, rather than just going, we're going to tweak this value, it looks better, everything is fine. We have to make sure that that little tweak actually means that it's still fine in terms of everything else that we're doing. And then additional challenge that we have in that area then is the fact that we need to have a lot more process knowledge. We need to have a lot more of an understanding of how every subsystem of the machine is functioning. And then we have to ensure that all of the variables that are actually in the system, which the OEM, for example, the machine manufacturer would verify for the parameters that they release, it's going to be good for what we're doing. What we do on the parameter development side is or material development, is we first create a customer URS. And this is a little bit difficult, I think, for some people because they want to just see what they can get out of the system. But at a certain point, you got to have a system where you're going to say, this is good, this is not good. We're either going to continue or we're going to reject this whole process. And that's why you create the URS with everything that you specify. Of course, this can be modified later on, but you need to have some targets so that you can create a budget and understand this. Because as you'll see in a second, the budget can explode. And the next thing that we really need to think about is validation versus verification. So what we mean by that is, I'm going to give a little examples. Like imagine that you have a stove, right? Just a very simple application. You turn on the heat and you want to understand what temperature whatever you're making is going to get to. So you do a basic simple test where you set the stove at 1 and then you measure the temperature, then you set it at 2, you measure the temperature and you keep going and you find some kind of a correlation and you go, okay, this is how this system behaves. So that's the validation step. Then the verification is when you're actually doing your work, you're trying to understand, is it still behaving within those confines? Now, you can't realistically do validation of every process parameter on the machine on a regular basis because that would take you 3, 4, 5 days. So what we do is we do a verification step where we'll, for example, in this example, we'll say, okay, at 100 degrees Celsius, the water is going to start boiling. So let's take a pot of water, let's put it on the stove, and let's see, is it actually fulfilling that requirement? Yes, it is. We can keep going. So, of course, we have to understand the assumptions that we make, and for that, we have to understand how the system behaves. The next thing is generally speaking, for the entire process, we have to find a way of freezing and defining everything that we do. So what we do is we call it the 5 M's of efficiency. It comes from lean production, and it's 5 basic steps. There's the man side, machine, materials, medium, and methods. And all of those are extremely important because you have to make sure that your people are trained well and that they're doing things in a repeatable way. You have to make sure that the machine is doing things in a repeatable way, that the materials that you're getting in are good, and this is something that we take for granted sometimes, that the environmental conditions are good, and that the procedures that we have internally are followed to the dot every single time that we're doing our work. And that has to be documented because there is unfortunately a lot of variability in the AM process that is operator caused, that is supplier based, supplier dependent, and we have to make sure that whatever it is, it's the same. So then after we do the development work, we go through the qualification and the validation, or before, sorry. So what is qualification? We divide the qualification into 4 separate steps, FQ, IQ, OQ, PQ. And this is, the reason why we do this is because we want to make sure that everything that's going to stay constant will be checked before, and then everything that we're developing is going to be done afterwards in what we call the PQ. So the factory qualification is something that you do basically at the OEM that's delivering the machine. Then the IQ, OQ, PQ is something that you do on site. The FQ, IQ is pretty much the same. You just want to make sure that the machine, when you push a button, it does something and it does it in the same way every time, that the button works. The OQ is when you push the button, you want to make sure that it gives you exactly the same value, so the validation aspect of it. And then the PQ is the aspect where you're actually testing whatever you want to understand, whether it be a material or an application, and then you actually go through the process of making sure that everything is being correct on the final results of the final application, final part that you're trying to work on. And then as you're going in production or as you're doing your R&D, you do some verification, which in this case, I gave the example of continuous sampling. And the last thing that's really important is the quality in aerospace. When we talk about quality, we tend to say that there's a good, there's a better, and there's a best. Well, in aerospace, it works a little bit differently. When you have some kind of a standard deviation of mechanical properties, as you can see in those gray markers, anything below that is bad. Anything within that range is good. And anything above that is also bad. The reason for that is because anything above that, even though it's better, we don't understand why it's better. And so it's not within our standard deviation, which means that it's a surprise to us. And that's what quality means in aerospace. So this is the funny example of how a lot of times aerospace customers will have a piece of software that comes from 1984. And you're going, why is this? Well, because it worked, it's always worked, and we don't have to revalidate it. So one example that's really nice to give is in terms of powder validation. When we're doing powder validation, we want to understand how the powder is behaving in terms of the sensitivity with respect to the process. So what that means is if you turn a knob, you want to make sure that if you turn it 5%, your results change by 5%. If you turn the knob by 5% and then your results change by 10%, then the sensitivity is twice as high, which means that this process can be unstable with regards to that knob, so we should probably freeze that knob. The next thing is that we want to break it down into the machine properties, the powder properties, the position in the build that you're making, so all of these things have to be documented, and then of course the powder evolution, which is the powder aging that we normally talk about. So after you do those first three, then we can actually get into the topic of powder evolution. There's a number of approaches of doing this. The typical approach is actually doing a test on 3 machines and 3 powder batches. Now, that's really important to understand because typically the machine variability is actually significantly higher than any powder variability that you have. That's not to say that the powder does not have variability, but what happens is that when you change your powder, it typically means that the variability of the machine increases, not the other way around. Because remember that the powder is actually something that you can't really change. So what we do in a hypothetical is this is how we would actually test it. So we would have 40 tensile bars per build, density cubes in order to measure the porosity, powder samples in order to measure the powder properties, and then you need a certain amount of powder. So based on that, what we would do is we could have a breakdown of different kinds of configurations. So different powder batches, different machines. So if we do the first simple test, which is we have 1 powder batch, which is realistically what customers usually do, we would test it on 3 machines. It would cost around $20,000, and we'd have around 120 samples. So the sample quantity is actually quite important because when you're characterizing a material, there are some certain requirements in aerospace for how many samples you need to test. And through this way, we can actually understand the machine variability and the powder aging. Now, the machine variability, like I mentioned, is the most important thing. So this is probably, coincidentally, the cheapest and also one of the best ways of doing this. When you go and increase the number of powders because you only have 1 machine, the costs automatically go up and the cost per sample go up, which is important because you need a lot of samples in the end. But what we do get to do is we understand the powder variability. Then the other variant is where we actually test 3 powder batches and 3 machines. And of course we could do 9 different runs, but it's going to be quite expensive. So in this category, we'll have about $40,000 worth of costs. You can notice that the price per sample actually starts going down, and we start understanding not only the powder aging, but also the machine variability. And then the final combinations are type D and type E, where we start actually shifting around between different variations of how many powders and how many machines we test, and we get a lot of data. However, the costs just keep going up. And so we have to kind of decide at a certain point, do we continue with this, or is this sufficient? Is the variability enough? And we can do some clever things, like for example, you run a build, and you take a look at how the variability is across the build, and based on that, you can see that there's a difference in terms of different machine parameters because machine parameters vary across the build. So then we can say, okay, we should maybe do some machine testing or we should do some powder testing. So this gets really, really expensive very quickly, and that's the materials development. So the other aspect that I wanted to point out is the production quality management system. This is a typical production flow in an aerospace production. The difference between aerospace and aeronautical being that aerospace are things that we put on satellites and aeronautical are things that we typically think of like a Boeing or a commercial application. On the aerospace side, we have a more black box approach. The reason for that being is that we don't have that many parts that we're building. When we're making a satellite, it's going to cost $500 million and there's going to be 4 pieces, for example. So you don't want to have to do a whole fatigue validation, machine characterization, powder evolution. That's not really necessary because we're not going to have that many parts. So we actually test a lot more parts in a destructive way. And then we actually have the flight-ready parts that go onto the satellite. On the aeronautical side, the complexity actually blows up. And the complexity increases on every aspect of the process. So the machine, the powder, the pre-production, which is the data preparation, also the post-production, the post-processing, and all of those things, if you think that they're stable, think again. Every one of those things has insane variability, and people are starting to learn that now, slowly. But it's very important to document these things and to keep in mind every part of this process actually has at least one document behind it. So these documents are really extensive, and that's part of the quality management system. So on the aerospace production side, like I mentioned, it's a small batch of parts. On the aeronautical production, it's a huge batch of parts, and the aerospace topics are usually treated like a black box approach. The aeronautical topics are actually dissected into every little aspect of the process as much as we can, and there's a document to record it and back it up, and this is actually obviously something that takes a lot of time, and this takes a lot of resources, and it's something that you have to do way before you commit to actually doing any kind of production on the aeronautical side. So this is also important for the material and parameter development. When we talk about parameter development, we like to look at it as a process. This process does change from one alloy to another, from one machine to another. So I'm going to try to actually give you a machine agnostic approach to this, and it looks like this. So what we do is we create the user requirement specification. We then pick whatever alloy we're going to use. We then create a specification for it. We do a feasibility study. This is where half the people are already lost, and they go, this is possible, maybe not, but they don't really know what variable is affecting the results. So they don't know really where to go in terms of improving their parameters or whether they should just drop the whole thing. So afterwards is when we actually make the decision, and we have a milestone there, a very firm milestone. Do we continue with the development or do we drop it? Because in reality, after the feasibility study, you're probably 90% of the way there, and you try to make the decision on whether we should validate the process, because there's not a lot of room for tweaking the parameters anymore. So when I'm going to be talking about parameter development, I'm actually only talking about the gray areas. The stuff in pink is just to give you an idea. It kind of looks like this. So we create a user requirement specification. We create a document that's behind that. We then take a look at whether the alloy that we're making is going to be possible by taking a look into the literature as well as the internal database that the customer will have, so to understand whether any additives will change the grain structure, whether they will reduce or increase the porosity or the cracks in the parts, the roughness. It gets pretty complicated, and so it's very nice to have a database. We provide help with that. It's a collaborative effort. Like, you can't really keep that to yourself. Machine manufacturers have that data as well because they, of course, do parameter development. And then we actually take a look at a powder supplier. If we find a good powder supplier, then we'll go ahead and do the development. But that's when we actually start doing the feasibility study. And the feasibility study we divide into 3 separate areas. Are there cracks in the parts? Which is already a difficult question to ask. Does the density meet the user requirement specification? And do the static properties meet the user requirement specification? So the reason why this is important and very, very significant for anybody trying to do this is because when we measure porosity, we need to understand the porosity in terms of the size and the distribution. And right now, there is no standard for measuring porosity, actually in any industry. So what we do is we create our own internal standards that we calibrate to. And those internal standards are very important because changing, for example, the polishing that you do on a sample, changing the etching that you do, changing the imaging that you use on the sample changes your results significantly, over 50%. And so when you have that variability, it's the garbage in, garbage out conversation where you're not going to really get any good results that you can draw conclusions from. And then finally, after these things are good, then we go, let's do the full material design of experiments, and then it gets very machine specific, alloy specific in terms of what we're going to do. So after giving you that context, which I think took a good chunk of my time, I think that's the most important thing, actually, because then when you do parameter development, that's when you actually sit down at the machine and you go, if I change this laser power, if I change this laser speed, the point where the laser is going to hit the powder bed, the layer thickness, only at this point is it possible to actually do that in a good and repeatable way. So what we had is an application which is a hydraulic manifold. I can't talk about the final end user, but we did this with Spartacus 3D, where the application actually fits in a 250 by 250 build area. And of course, the first thing that we had as resistance is that titanium cracks. It's not possible to build something this big. Well, I think it is, and so we went ahead and did this. Of course, you need to have better powder control in terms of the oxides. You need to manage your residual stresses better. You need to understand how the process is going to affect your fatigue results, which is the most expensive part of this whole thing in terms of validation. And you need to make sure that the post-processing is minimized. So the first thing that we did is we actually took a look at the impact of this massive geometry on the mechanical properties. When you have a lot of area that's being exposed per layer, the statistical defects actually increase in the process. And that actually has a direct impact on your fatigue, but of course you're not going to be testing that every time you run a build, because that means that every iteration is going to take about 4 months to do. So what we did is we first tried to understand the scattering of these results in a way that doesn't require us to build the whole manifold, and reduce the number of reduce the residual stress in the application, and then also reduce the number of inclusions in the parts. Now, when we did that, we first took a look at the actual distribution of the geometry. So when you take a look at a simple graph like this, we first try to analyze, there's this little area where when the exposed area per layer is very small, what happens is that the material overheats. Now, titanium specifically is extremely sensitive to that, because if you have a laser pass and the laser pass is a little bit off and it overlaps with something that was done previously, the material begins to boil and you have porosity. So we have to be very careful with that, where we make sure that the exposure area between layers is significant, that you will not get to this lower point of boiling. Then you have this sweet spot where it's shown in the white. And then you have this area above that where the statistical defects increase because of the fact that every time you're exposing something, the splashes are going onto another region of the part, and the properties of the final part will actually go down. And then the next thing that we look at is actually where the area in the exposure changes from one layer to another, because that results in volume jumps. And volume jumps on the surface are not a big deal because, well, no pun intended, sorry. On the surface are no big deal because of the fact that we can post-machine those geometries. But when we have something like a hydraulic manifold, you can't machine the insides. And the answer isn't easy in the sense of we're just going to do extrude hone or some kind of polishing, because you still have to verify all those surfaces. So what we do is we try to actually focus on smoothing out those peaks by doing some clever exposure strategies. The next thing that we look at is, after defining the entire volume of the part, we take a look at the surfaces. Now, in a typical laser powder bed fusion process, when you take a look at downskin areas, you have completely different parameters from the vertical walls and the upper facing walls. And those kinds of parameters lead to these kinds of defects. These kinds of defects are actually subsurface porosity that occurs in the process because of the fact that the layer is just at too steep of an angle. Now, Velo 3D, for example, has a solution where they're building with 5-degree angles. The laser powder bed fusion area is focused right now on building something between 15 and 20 degrees. But when we talk about the angle, we have to talk about, is it possible to build? In other words, will the machine just crash? And then the other aspect we have to talk about, is it actually going to meet our mechanical properties? And in the case of the mechanical properties, 15 degrees is not really doable because you have these kinds of effects. So what we did is we redesigned the parameters so that we can remove this subsurface porosity. And at the same time, we focused on making sure that the roughness in the geometries on the downwards facing areas, upwards facing areas is actually more homogeneous. Because when it's homogeneous, then the post-processing costs actually go down. So we defined these critical to quality regions. And we went through the designers over, I think, like 10 different iterations in order to improve the internal channels, to minimize those angles, to make the area self-supporting. So even though here, you can see that there's a horizontal structure, orthogonally speaking, when you take a look at it from a 90-degree perspective, it's self-supporting. And where it wasn't self-supporting, we had to keep in mind that we have to make it machinable. So then, after we did the parameter development, this is what we got. So you can actually see that the transition between these downwards facing areas and then the upwards facing areas is very homogeneous, and this is straight out of the machine. And then we also, of course, tested those regions to make sure that the porosity is good, and it was. It was actually, I didn't expect this, to be honest. So just to conclude, the areas of application that we look at in terms of parameter development are, I think, different from what customers typically expect. And what we try to focus on is actually application-specific parameters. However, those parameters have to be validated, keep in mind, and that's quite expensive. The second thing is that when we work with organizations, we notice that the largest deficit is actually in their quality management system and their process knowledge. And the process knowledge is something that you can outsource or you can keep internally, and I would say you should do both by building, for example, a very robust FMEA. However, we have to accept the fact that any person working on the operational side will probably be there for 2-3 years, and then they're going to want to move on with their lives. That's the generation that we're in right now. I'm a millennial as well. And so we have to make sure that the system is redundant for those things, because we can't just have this knowledge uptake and loss all the time on a regular basis. And then when it comes to the business case, I think you need to take a look at all these aspects before you commit to developing a project, because otherwise you're selling yourself short, you're disappointing your customers, and you're not really sure where you should invest your money in terms of the future growth of your company. So that's it. If anybody has any questions, I'd be glad to take them. Thank you.